Hey guys, how's it going? So today actually we're going to be taking a look at adapters. So adapters are quite similar to LoRa in that these are what we call parameter efficient fine-tuning technique. So they try to introduce some sort of like learnable parameters upon the pre-trained model. These learnable parameters are going to be optimized during training. The good thing is that the introduced learnable parameters can be as little as 0.1% of the pre-trained weight. So we're talking about something like 1.2 million parameters. So it can be quite efficient. So as usual, what we're going to do today is that we're going to cover the source code from the late Llama. We're going to write the pseudocode to solidify our understanding about this technique, as well as we're going to cover the paper so that you guys get to understand how this technique work in much more detail. So this will be our final wrap up with these recent techniques. They're not necessarily recent, but I'm saying that they've been quite popular because of we find them to be useful in this age of LLMs. So we covered pretty much everything here, like GPTQ. We covered the pre-training. We covered the sparse GPT. We looked into LoRa yesterday. We're gonna look into this adapters today, and that will be it. So in the next video, I'll tell you guys what we're gonna be looking into going forward. So without wasting any time, let's get into it. So coming to the paper, the authors state that we're going to be appending a set of learnable adaptation prompt as prefix to the input instruction tokens. These prompts learn to adaptively inject new information to the pre-trained model. So how you can think about this is that given the input, we're going to be pre-appending some sort of like a learnable tensor, and this learnable tensor is going to be added as a prefix. And we're going to be optimizing this learnable tensor during the backpropagation. So for you to better understand this, let's take a closer look at some of the previous concepts. There is a concept called soft prompting. So how you can think about this is that this is just a learnable tensor in which we can actually pass this towards the full connected layer. So this is just to ensure that we have a compatible dimension with the input, because this soft prompt is going to have to be added with the input. But the question still remains, why do we need soft prompting? So the idea behind soft prompting is that we can actually be able to adapt our model to fine-tune data, so new information. So because of this, soft prompt and the concatenated input will be passed towards our transformer blocks. So when we're going to backprop, we can actually be able to optimize these to the new information, right? So that's the core idea behind soft prompting, but we will see how it actually relates to the paper. Then the second concept that we can look into is the adapters. So how you can think about adapters is that these are just modulars, right? By modulars, I mean these are just full connected layers, and you can have non-linearity here, and you can have another full connected layers. So the reason they are like this is because of we can actually project this the first full connected layer to a small dimension, and we can reproject the second full connected layer back to the original dimension. So we can think here we have 500, we project this to 10, and we project it back to 500. So doing it this way, it's more parameter efficient. You can do the maths and you will see, than actually projecting 500 to 500. So you're going to have more parameters. But anyway, the question still remains, why do we need adapters, and why do we need to add something like this at the transformer blocks? So the intuition is that we can be able to learn new fine-tuned data, and we can also, because of their added after the transformer block, we can actually be able to learn the pre-trained information within these adapters modules, right? So that's how I think about them. But now, given that information, let's look at how this paper tried to combine the knowledge or the papers from the prefix tuning and the adapters uh, to bring their paper. So now let's look into Llama adapters. And most importantly, try to understand how the authors have integrated the concept of prefix tuning as well as soft prompting. So there's one thing that looks familiar to us, which is this learnable adaptation prompt. So we know that this has to be a prefix and it has to be added to the input, and it will be optimized during the backpropagation because it has to learn new information during the fine-tuning stage. In this case, we can see that the authors have represented this prompt with the dimension of k by c. C denoting the feature dimension of the pre-trained model. Then k is going to be a hyperparameter that we define. And this pi will be concatenated with ti denoting the mth weight tokens. And it's going to be concatenated across k by m while we still retain the feature dimension, which is c. And I like this intuition from the author, in which they say that in this way, the instruction knowledge learned within this prompt can effectively guide TI, which is the word tokens, to generate contextual responses. So before I throw another concept at you, such as zero-in attention as well as gating mechanism, let's try to understand how the input will be transformed across the transformer block as well as the learnable adaptation prompt. I think if I try to visualize these concepts, it will be much better for you to grasp this concept. So for now, let's try to imagine that we have an input like so, and this input here will have to go through the self-attention, right? And the self-attention will give us the output. And this output here will have to be added with something. For now, I'm just going to write question mark. So you still remember I used to tell you that we needed to add the prefix at the beginning, like with the input, right? But because of the authors are trying to integrate the concept of adapters as well as soft pumping, they are not adding it here. Instead, they are adding it after the self-attention mechanism. And how they are adding it is that they're aiding it by actually applying the self-attention, right? So they call this zero innate attention, right, on the prefix. So you can think of this as the prompt on the prefix. So you're gonna apply that. Then they're gonna actually also have something they call a gating mechanism, which I'll tell you the intuition behind this, right? So this is how they're going to add that prompt that I've been talking about to the output of this self-attention mechanism. So before I explain the zero innate and the gating mechanism, let me explain to you how will this self-attention of this prefix will be applied. So for now, how we can think about this is that we can have a prefix. You still remember the dimension of this? We said that it will be, if I'm not mistaken, is k by c, right? And this will be linearly projected, so nothing different. We all know this because this is the attention mechanism. So it will be linearly projected and will be passed within the k, or as well as what is it? It's going to be the v, then the query, which is going to be coming from the original self-attention of the frozen model, right? So the query will be coming from here. Then here we're going to have what we call the scale dot product. So this is the same attention, scale dot product. So this is the attention that is going to be past the prefix here. So this is what I'm representing here. It's just here I'm expanding it so that you get to understand how it's going to be implemented. So don't worry if you don't understand. We're gonna have to go through this thing in a much more detail, right? So I spoke about two concepts, right? I spoke about gating and I spoke about zero innate, right? So now, what's the intuition behind why do we have to initialize these by zeros? So how you can think about this? Imagine if we were introducing parameters like prefix, like these are learnable parameters. If you're about to randomly initialize them, then when you start your training your loss will be high because of you just randomly initialize these parameters. Then the learned knowledge within your pre-trained model will be overshadowed because you're introducing these random things here. So how about you just when you start your training, just initialize everything at zero so that you have the original weight. You're starting with the original weight. I think that's better. So your loss will be probably not that bad because of you already have like the preserved knowledge from the pre-trained, right? So it will gradually increase. Then you might be asking yourself, okay, cool, I get that, but what is this gating mechanism? So the gating mechanism is going to be able to control if like this self zero innate self attention mechanism should have an impact as we added here should have an impact, because when we start, right, we starting with zeros, so it's not supposed to have an impact. So the gating mechanism will be controlling the impact this prefix self attention will be having within the output of the self attention. When we start, it's not going to have, because of we're going to initialize this with zero, right? But as we continue to learn, as we progress, this here will be learning and will start having impact in this gating mechanism. It will be adding information from this prefix self zero init self attention. Okay, and that's what it is to this. I know that probably maybe you thought this will be added here, but I was trying to make sure that you understand the concept first of soft trumping prefix before it's like throw you at this concept. But really, this is all it is to this paper. Now you have a good understanding of gating and why we need zero in it, and how the prefix zero in it attention will be implemented, and how we're going to be adding these knowledge from coming from the prefix as well as the self attention of this pre-trained weight, right? So we're just gonna do an addition here, right? So now let's try to formalize our explanation with maths notation. So given this self-attention, we are going to compute the attention score for SK. So SK is going to be denoting the length of the prompt. Then this SM here is going to be denoting the length of the word token. So given these attention token, we just need to compute their probabilities using the softmax. So this is going to be the softmax for the SK as well as softmax for SM, which is the weight tokens. Then the attention of the SK will be multiplied by the G, which is the gating factor. So like I explained, this will help us to know how much information should be contributed. So if like we still have zeros, then we shouldn't contribute a lot. So you can think of this GI here will be also a learnable parameter in which it will keep on learning. It will progressively learn and understand how much information should be added, right? So I think that's how I think about this. So to explain this in a much more intuitive way, so you can think of like we're trying to understand how much information this prompt is going to be contributing to this TI, right? Then after we have this output here, we are going to we're going to have a linear projection layer in which we're going to multiply this Si by V. So it's just a typical attention mechanism. And I think also the dimension makes sense because of here we're going to be having K by M, and V also has this dimension is going to be K by M. So I think this will work out. So yeah, and yeah, I think I have to say this is it to this. Honestly, going down, I think it's just like empirical results or and like evaluations. So yeah, I think that's what it is to this. So I'll try to solidify our understanding by writing the pseudocode. So this way I'll try to condense everything in like less than 30 lines of code so that you get to understand. Then after that, we're gonna look into the lightning source code so that you get to understand how this is implemented in a more like production way. So let's go into it. So coming to the pseudocode, what do we have guys here is the learnable adaptation prompt. So we're going to initialize this embedding table with the prompt length and the feature dimension. So the prompt length is something that we define, then the feature dimension is going to become the embedding size of the model. Then we have this zero innate attention, which is the gating factor. So this is going to be the trainable parameter. So we're going to initialize this to zeros because when we start, we want to stabilize training, right? Then we're going to have these attention matrices, the key query and value. So I needed to destructure them so that you will see how they're getting applied on the attention of the prompt. So we're going to pass the input as usual to this, and we're gonna get the query and key and value because of we splitting by the last dimension, and we're gonna pass these query and key to the self attention, so to calculate the attention score for the weight tokens, right? Then we're gonna have to do the same thing that we did, but this time for the prompt. So here we're gonna pass this and split by the future dimension. So this is going to be the prefix key and the prefix value. Then now we compute the attention score for the adaptation prompt. So, but this is the main thing that I want you to look into, which is we passing the query of coming from this the word token attention, right? Alongside with the prefix key and the prefix value, right? Then we're gonna get the prefix output. Then we multiply the prefix output against the gating factor. So, and then we're gonna add these to the output of the attention. So that's what we're gonna project. So yeah, like I said here, add a learnable gating factor so that we can adapt or control the importance of this prefix output in the attention mechanism. So as you guys can see, it's quite straightforward and that's all it is to this. So you can see that my code is quite short because I didn't include things such as attention head. I just wanted to keep it as simple as minimal so that you guys, when you go through the pseudocode, can actually get the idea right away. So now if you want to understand the detail, let's go and look into the source code whereby you will see the nitty gritty of how this is getting applied. So I think that way you'll actually be able to understand much more deeper way. So coming to the source code, we're going to be covering this adapter.py file. It's within this late llama folder. Then we're going to be looking into another adapter.py file. It's within this fine-tune. So this file here within the fine-tune folder is going to be responsible for training our or optimizing our adapters. So we're going to keep the pre-trained weights frozen. I'll show you how we do that. Then this file here, which is within the lit llama folder, is going to be the one which is holding the core idea behind the adapters. But with that said, I have to say this code is quite simple in a way that they have used the same code that they used within the pre-training. So we covered that code. So hence I'm saying it's simple. So, but I'm still going to explain everything. I'm just like telling you that so that some of you guys will see that this is quite something that we did cover in the previous videos. So as you can see, the main thing I think we have to add is that we need to compute the self-attention for these adapters. So this learnable parameter that we added. But other than that, most of the things here you will definitely understand because we have been covering them in the previous video. Anyway, we're gonna start explaining this casual self-attention. So the first thing that we're going to do is to batch the linear projection of the query and key and value. So in the most source code, you'll see that this is actually replicated 3 times and people will write query, key, and value. But in this case, we're just doing it in one line by multiplying the size embedding by 3. So we're going to split this when we're doing the forward pass. I'll show you how we do that. Then this is going to be the projection layer also. I'll show you how we also apply this after applying the self-attention. This is also something that I did not mention in the paper. Actually, let me zoom in. Just gonna, yeah, I think that's fine. So this is something that I did not mention in the paper. So what happened is that we need to apply the adapters at like topmost blocks, like at the top like blocks. So the authors, the intuition behind this was that this, doing it this way, we better tune the LLMs like representation with higher level semantics. So that's why we have to do it this way. Anyway, we have this self adapters. So this is something that we saw in the pseudocode. So we have this adapter prompt length, and we're going to have the embedding size. So this prompt length here is something that we define. It's a hyperparameter like so. So right, then we have the gating factor. So this is going to be initialized to 0 so that we stabilize training when we start training. Like I said, the intuition behind this is just to ensure that we do not like start our training with like some random numbers. So this will like make our loss to be quite high, right? So this is we when we come to the forward pass, we're gonna have this input, and we're going to destructure it by batch by by sequence length and by this dimension here, which is going to be the dimension. And then this is what I was telling you about. So you're gonna pass this input here, and we're gonna split it by the dimension. Like this dimension means the last dimension because of these three of them here. So it's gonna be two. So we're gonna split this by this embedding size. So we're gonna get query key and value. Then what we need to do is that we need to apply multi-head self-attention. So what we do is that we're gonna divide the embedding size by the number of head. So we just gonna what is it? We're going to apply the view. So you can think of this as like we're trying to reshape our dimensions to be batched by sequence length by number of head and head size. So this is like how you can think about this is that we are representing our dimension into like small pieces. So like by small pieces I mean like number of heads. So it's like, if you multiply these two, you're still gonna get like C. So in this case it's just like we're representing it in like small pieces. Like that's how I think of it. But so I'm trying to explain it in a much more easy way for you guys to understand. But yeah, that's how we do it. So we apply self-attention on these small head or small pieces. Then this is going to be the rope encoding. So we apply this. So this is going to be, it's not similar to the positional encoding. So we need to apply this on the layer wise. That's that. Then this is something that some of you might not be familiar with, but it's something that we apply because of this is based on PyTorch 2.0 optimization kernel. So we're doing it this way instead of like doing it manually. So this is more efficient because there is a lot of optimization that they did, such as flash attention, right? Anyway, we're going to pass our query and key and value, and this is gonna like do the dot product of like the query and key as well as like the value. So how you can think about this, I'm just gonna make example so that most people can understand. So let me, yeah. So this is like the dimension that we have. So we have something like this here. So we're gonna be having, what is it? It's gonna be batch by T by number of head by head size, right? So when we come here, so we're gonna provide these. So this scale dot product attention function, it's gonna do the transposition function for you, right? So you don't have to like do those things anymore. So it like kind of like handle everything for you. So I'm just gonna copy this. I feel like some people understand better when they see these dimensions. So we can think we're gonna have the dot product. So as usual, we do the dot product between the query and the key. So but here we can think of like it's gonna apply that transpose function. So that the dimension work out. Then this is gonna give us what is it? So the last thing that I Oh, the last thing that I forgot to explain, sorry about this, is that we're doing the transpose of the first and the second dimension, which makes sense. So you can think of here we have number of head and T is gonna come here because of you want to compute the attention of the tokens, right? Not the attention of the number of heads. That will be something else. So you wanna bring T here. So T represent the number of tokens. So the number of tokens and their dimension. So this makes sense. So but we still have T because of you wanna transpose these two here. So you want to do the matrix multiplication between these two. So this is fine. And then the output that you're gonna get, because now you did the matrix multiplication between these two. So what you're gonna do is that you're gonna have to get the attention score between the tokens. So your dimensions now are supposed to be batch by number of head by T by T. So this T, it tells you like the score between each token. So you can think of like given a sentence, like each weight, it's gonna like attend to one another. Like that's why here we have T by T. Okay. Because of here, we also provide the what is it? we provide the value. So we're gonna need another dot product here. Okay, so this dot product is gonna be b by number of head by t by hs, right? Because of that's what v is like. We haven't done anything to this. So the output that we're gonna get here. So you can think here we're gonna have a matrix multiplication. Then we're gonna get b by number of head by t by uh, head size. Because of this T and T, they go into cancel one another. Then you're gonna be left with this H and this T here. So now you have your dimension is like this, right? So I hope that makes sense. But the reason I'm showing you these dimensions is because I want you to kind of like understand that this thing like helps you a lot. You had to do all of this thing that I did manually when before PyTorch introduced this, right? Anyway, like I explained you, the intuition behind this was that essentially, as the paper stated, that they apply these adapters at like the topmost layers. So when the block size is greater than or equals to the self adapter start layers, that's when we want to start applying this adapter logic. So this is because the authors state that it better tune the language with higher level semantics. Okay, then we're going to be having this prefix right here. So this is going to be the prefix dot weight. We're going to reshape it to this. So what we can think of we're doing here is that we're just adding a dimension here, which is, yeah, which is one. Then this is going to be soft dot prompt length. Then this is going to be the embedding size. So here we're just saving the embedding size, right? No, sorry. We're just saving the adapter prompt length. So this is going to be that. We'll see how it's getting used. So we're doing the same thing that we did in that we're getting the query and the key and the value by passing the prefix to this self attention, and we're gonna split by the embedding size. So that's what we did. But we do not want to use the query from this. We only care about the key and the value. So we also have to do like the multi-head attention with this prefix. So that's why we needed to re reshape our data to this, right? Then that's what we have. Then we're gonna pass this key and the value within this other the self attention mechanism, in which we're gonna compute the attention scores. Then when we are done, we're gonna take the output and multiply by the self-gating factor, and we're gonna add this to the output of this attention coming from here. Okay, so that's that. Like that's like the output of this the first self-attention of the, like we said, this was the word embedding, word length or word tokens. I mean to say. Then this is the attention for the adapters. Okay, that's what we have here. Then we just gonna project the output, right? And this is, we're gonna get b by c by b by sequence length by channel, and this is what we're gonna return. So it's pretty much like something that we've been like going through a lot. So it's not that hard. The only key thing is that one has to understand is that the query of this weight tokens has to be passed here. So you can think of this more like a cross attention. I don't know if some of you guys have watched my segment anything paper and source code. So they pretty much do something like this, but it's similar to what we call cross attention, because we need to pass the query coming from this attention, and we need to pass it here. Then the key and the value, it's coming from the prompt key and value, right? That's what we do. So, and that will be that. Then now let's look into this block. Now coming to the block, how you can think about the block all the time is that look at it from the perspective of a block is a layer, and within a layer there's sub layers, and those sub layers are self attention and there is multi-layer perceptron. All the time before a sub layer you need to apply the layer normalization, and after sublayer, you need to apply what we call residual connection. So that's what it is to this block thing. You can replicate it as many as you want, especially if you're training like very, very deep models. So you can replicate this block, and I'll show you how we do that. But in this case, think of it like we have an input, and the first thing that we need to do when you get the input is to apply the layer normalization. In this case, this is going to be the root mean squared layer normalization. I did explain the benefit why we're using this, not the other layer normalizations, and what are the benefits of using the root mean squared layer normalization. Anyway, after applying this layer normalization, you need to pass the input to the self attention. So this is the first sub layer. Then when you're done, you need to do the residual connection, right? Then, when you're done with the residual connection, you need to apply the second layer normalization to the output after you applied the residual connection. Then you're going to apply this multi-layer perceptron to the output after applying the layer normalization, right? Then you're going to apply the final residual connection. Then you return, right? So this is how you kind of like think about it. Then yeah, that's how it works. But anyway, we going to be having this Llama class. So this is where we're gonna have to make the predictions, like we have to return the logic. So how you can think about this is that we're going to be having this head. So this head is gonna get the dimension, like you can think of like it's the final stage, and it has to return the probability. So hence here we going to have a linear layer takes the embedding size, and it's gonna project to the vocab size because it's gonna make the predictions across all the weight distribution. Then we have this transformer block. So as you can see that we can replicate this block as many as we want. Hence we have this for loop. Then we have this embedding in which we're going to have the vocab, and then we're going to have the dimension of these tokens. So you can think of like when we have a token, we can actually we go into when we have a token, right? We can pass it within this embedding. So think of this as a dictionary to get the dimension for that token. Then this is going to be a root mean squared layer normalization. So within the forward pass, we get the tokens, but we get them as a batch. You can see that they do not have an embedding size, like they do not have an embedding dimension. So we need to give them the embedding dimension. So that's why we're gonna call transformer.wte, because of this is the function here. So we're gonna give them this embedding size. Okay, then what we have where we were okay, we were here. So we're gonna apply we're gonna pass the input towards the number of blocks. So that's why here we have a loop, because remember that we created a list of these blocks. So we're just gonna keep passing these input within these blocks. So you can think about this as like as we pass the input to each block, the output from the first block is gonna become the input to the next block. So it's just going to repeat doing that until we get the final output. But once we have the final output, we can apply the layer normalization and get the predictions because of this is going to give us the the predictions here. I think we said here. So yeah, these are the logic. So yeah, so we can actually compute cross the loss function, so cross entropy based on this logic, and I'll show you how we do that. But this is something that I did explain, especially in my pre-training code. So that's why like I'm not putting too much effort, because I feel like I'm just repeating myself. The main idea, honestly, guys, I'm not gonna lie to you, was I wanted you guys to understand the adapters. That's like the main goal. So the main question still remains. Some of you might be asking yourself right now, like, but how do we then train the adapters? Like, because of it looks like here we have these blocks, and are we not gonna be training Llama from scratch? No, we have this function here. So you see this function, so it's going to be the one that help us not to actually not to train the llama layers, to only train the adapters parameters. So here, how you can think about this, we're gonna pass the model, and PyTorch, when you pass a PyTorch modular, so you can call this function called the named parameters. And then this name parameters, essentially how you can think about it, it allows you to get, when you have like a class like NN module, you can like get these things that you defined within here. You can get all of these things. So like adapters, gating factors, all of these things you can get, right? So you can think of like we got all of those things, and if it happens that one of the names is actually the adapter WTE is within this name, or the gating factor is within this name, then we're going to set the parameters to true, because this will equate to true, right? So this is going to be true. But other than that, everything will be false. So which means that we will never train the llama weights. They will be frozen because of the gradients won't be computed because they are equals to false. Whereas the only thing that we're gonna be computing, it's gonna be the adapters and the gating factors. So just to remind you, these are where we define these things. So yeah, we define them here. So this is like the adapters and embedding torch dot and then parameters. Okay. So yeah, we added these within multiple blocks. So because of we call this multiple times, so it's gonna apply across. So now let's go to this code here called adapters.finetune and try to understand actually how we train. So within this main file, we're gonna need the pre-trained weights. So you can think of like we have like the weights of La Llama on the folder called checkpoints, and we're gonna need to pass this path so that we can actually be able to load them. Then we're gonna also need the data directory, because we're gonna need to load the validation and the trained data set. Um, then we're gonna use this Fabric library coming from the Lightning AI team. So I think they have done a good job in that they have tried to combine all of these cool tools like from Deep Speed strategy, from the PyTorch team. I think this is called the FSDP strategy, and they have integrated all the precision types. You can have like BF 16, so all of the stuff are inside there. So it's a very neat library, especially if like you wanna have distributed training, you can check it out. We're gonna use this function called loaded dataset, in which we're gonna pass the dataset directory. So this is gonna return the validation and the trained dataset. So this is quite easy to understand in that it's just gonna load the dataset from the data directory. Okay. The interesting part here is that you still remember this function, in that after we have loaded the model and the checkpoints, we have to make sure that we do not train the weight of the llama, right? Meaning that we only have to optimize the adapters parameters, because of those are the ones that we flagged as trainable. Otherwise, everything has been set to false. So we do not want to track their gradients. So that will be that. Then the optimizers will be using Atom, and we're gonna pass them within these train function. So this train function is gonna be called from here, right? So this is like we're gonna be going through the number of epochs, and we're gonna get the batch given the data set. So this data set, it's gonna return the targets and the input IDs. Then we pass the model, so we know that our model returns the logits. So this is this part, we covered this right here, right? So it returns the logits, but based on these logits, we're gonna pass them within this loss function. So this is gonna be the cross entropy. So the cross entropy, given it like the logits and the targets, is gonna return the loss. So then you can do the backwards pass. Then I think this is just for matrix and all of that. But yeah, the training stuff is always straightforward. Then I think here is just to update. We compute the gradients and do the updates. So because of but the only updates that we're going to do is we're going to be updating or optimizing the weight of the adapters only. Okay, and yeah, I think that will be it to this adapters file. Yeah, I think we have covered like the core thing that we needed to understand about the adapters. And yeah, I still have to say that, however, these things are quite the same as we looked into LoRa yesterday. They're very, very much the similar in terms of like the implementation. Also, I have to say that the intrusion, some of the stuff are quite similar. And so, for instance, with LoRa, then we needed to ensure when we initialize the first matrix, which is A and B, we needed to make sure that when we start, those are set to zero because of uh, we wanted to stabilize the training, and we wanted to make sure that the loss does not skyrocket when we start training. So it's the same thing that we did with the adapters. So the intrusions, the main intrusions behind certain things, they're pretty much the same, just like maybe slightly different stuff. But anyway, that will do it from me, guys. Yeah, I think that will be it. We covered more, and the main thing that we're supposed to cover was like the code. But anyway, I really appreciate it, guys, for tuning in. I'll see you guys in the next one. Thanks. Bye.